And of course, you have to do this pre-processing. We pointed out that you can calculate all these pairwise similarities ahead of time. Um, that wouldn't work actually if you had a lot of items and you had to calculate, for n items, you have to calculate n squared similarities. That's probably prohibitive. However, the number of items which actually have enough users in common to be able to calculate a reliable similarity is much smaller. So, and another important comment is that item similarities are supposed to be more stable than user similarities. Remember, the user similarities are the ones we discussed in the previous unit. Um, then we have in this neighborhood, and exactly how big that neighborhood is. It comments is we're typically quite small, but I don't quite. I say I have no. I don't know, and I don't see any strong documentation of those statements. As I've already discussed, you do not have to actually have n squared, where n is the number of items, because many item similarities cannot be calculated. So you use some ingenious sparse storage, so you only store the ones that can be. You can also toss any things which are far apart. You just if things of a very low similarity or negative similarity, that's equivalent to not knowing the similarity, because we're not returning items that Alice hates. I don't. If you did, then you would actually want to keep these negative similarities, because then you could say, "Hi, Alice. We think you'd like this, and we know you. We also think you'll hate this. Why don't you see if we're right?" That might actually be an interesting marketing tool if you gave her what she wanted and what you think she doesn't want. That would be pretty interesting. I'm not certain that's actually done. Anyway, that's the brilliant idea of the night. Um, so we'll see how that. We won't do anything about that now. And there's lots of studies about the neighborhood size, and sometimes they get funny answers. I had a paper which I once read and commented on, which had that feature of suggesting very small neighborhood sizes. Then, if you look at the ratings, we have the explicit ratings. When you go in there and read the book, when you look at, I don't know, Amazon. Many books have thousands or tens of thousands of ratings, and those tend to be rated on a scale from 1 to 5 is very common. 1 to 7 is also common. These are so-called Likert responses. They go from bad to excellent in various gradations. And as we remember, we take out the grumpiness factor, namely whether somebody only ranks things from 1 to 3 because he thinks 4 and 5 are just don't exist in this terrible world we live in. You scale that out by taking out the mean and scale by the variation of that user's scaling. There were studies which showed that the 10-point scale was better accepted than the movie domain. And actually, when we looked at the Kaggle site, I think we looked at the joke recommender system, where a continuous scale was used and a nice graphical input bar to set the scale. And that sort of increased the fun of doing all of this and was proven to be quite successful. As far as I know, there is no people have studied whether it's better to use finer resolution, and I believe 1 to 5 is fine. There are enough uncertainties in this prediction, and most important, there are enough users we sum over that we don't actually have to get it very accurate for any one user, because you're getting your accuracy from lots of users, and that's for the item similarity. There's going to be lots of items for the user similarity. Of course, users are not willing to rate many items. I'm afraid I never rate things on Amazon. Essentially, I let other people do the ratings. I just do the browsing, and so you need to have better citizens than me who actually do ratings, and you need to persuade that. And Amazon's always sending me emails telling me to rate the buyer that I just bought something from, and I sometimes do that. but we know the buyers will get very unhappy unless they're ranked 5. I mean, if you look at the ranking of buyers, they're very high because people are scared to rank those too low. That's an important feature of any ranking system, that you get grade inflation or whatever it's called. Um, so there are also implicit ratings. Um, Namely, if you buy something, that's presumably, it's not necessarily a positive rating because you may hate it after you bought it, and then you may sometimes you go back and write a ranking which is terrible, but often you just give up and try to suppress it and not mention it again. There are things like how long you spend on a page, which page you views, what things you download. These are all implicit ratings. And the advantage of them is you don't actually have to persuade the user to do anything. You see, I'm getting implicit ratings of these videos by just looking at the Google Analytics, which tells me how often people read the, I mean, how much time they spend on each video. And the videos that presumably people spend a lot of time on are either impossible to understand or brilliant, and we can, but that's whereas the ones they spend no time on are either trivial or incomprehensible. So we have to. So probably the first category is the better category. So at least I can use implicit information to try to improve this class. And you obviously all of this is in a real system that's all put together in some giant package. As I said, Netflix has 100 items in this giant machine learning system. At least the one that won the competition did. I assume Netflix has even more these days. So, and now we move on to some general comments on these technologies and the Kth nearest neighbor algorithm. And that's the end of this lesson. Thank you very much. This is Geoffrey Fox. Let's go on to the next lesson.